going to be a disc to make it a little different than your laboratory. A solid 1 kilogram disc of radius 1/10 of a meter is released from rest on top of a plane inclined at 30 degrees above the horizontal. What will be the speed of the ball after it rolls 1 meter down the plane? Okay. So let's go ahead and draw this, and here is our disc. So I'll kind of make this look like a disc to remind me.
So 3D.
Yeah. So this disc will be rolling down, so I'll just indicate the rotation direction. And we need to figure out the speed of the disc after going a certain distance down the plane. So this distance here, I guess I'll just call that distance D, is 1.0 meters. Okay, we know this is an angle of 30 degrees. So let's go ahead and see if we can figure out how fast it'll be moving. So whenever there's a change of potential energy, you should consider using conservation of energy. Whenever there's a change of speed, consider using conservation of energy. So in this problem, I'm going to use conservation of energy to solve. I'm going to call a point up here my initial point. I'm going to call this point my final point. The conservation of energy equation says when you add up all of the kinetic energies, which is translational, translational is the kinetic energy of the center of mass, plus rotational, and when you add up all of the potential energies, the result must equal to the work done by non-conservative forces or the work done by other forces. So in order to figure out the potential energy, I'll just figure out what my forces are. So with my forces, we have the gravitational force acting on this. So you know that's going to be a potential energy contribution. We have a normal force acting on this. And then we're going to have static friction acting on this. And static friction, so the interesting thing is we have to figure out the tendency of this to slip. If this weren't rotating, this point at the bottom of the disk would slip down, which means static friction is in which direction? Up. Good. And what's funny is it's static friction that creates the torque that causes it to rotate. Like if we just go back to last week with torque, you know, if this were the center of the disk and this were static friction, static friction is a torque that makes it rotate, which is why if there were no friction on the plane, it wouldn't roll at all. It would just slide down the plane. The static friction is making it roll.
Shouldn't friction be pointed down?
Nope, because again, ask the question, if this were to slide down, what opposes the direction of slide? It's the friction. So that's how you analyze that. Okay? It's counterintuitive, but that's how we do it. We'll say it's negligible. Rolling friction, in this case, rolling friction, so in that situation, yeah, in this case, rolling friction would be a contribution in that direction as well. But we're neglecting rolling friction. Okay. All right, so we have gravity. Since we have gravity, that's going to be potential energy. We have static friction. In laboratory last week, I said that consider static friction. Instead of finding the work done by static friction, that's already included in the change of rotational kinetic energy. So for static friction, so when you have things that are smoothly rolling, instead of work done by static friction, we're going to substitute rotational kinetic energy, okay, for things that are smoothly rolling. And then the normal force is always perpendicular to the direction of travel, so the normal force would be a work done by the normal force, and that's going to be 0. So the reason why I created this catalog was so I would know what to put in my conservation of energy equation. So it's translational kinetic energy, rotational kinetic energy. Since I have gravity, this is the potential energy due to gravity, and friction is causing it to rotate. So I'll have the change of kinetic energy. Oh, I already got that. This was the friction contribution. And this is equal to 0 because nothing else is contributing to work. So here it's 1/2 mass of the disk, speed of the disk squared, minus 1/2 mass of the disk, initial speed of the disk squared, plus 1/2 rotational inertia of the disk, final angular speed of the disk squared, minus 1/2 rotational inertia of the disk, times initial angular speed of the disk squared, plus mg final height minus mg initial height is equal to 0. So let's look at what our different terms are. It starts from rest. So our initial speed and our initial angular speed is 0. It starts off at a certain height above our bottom. So I'll just go ahead and create a coordinate system through our center of mass. And so our final height, we will call that 0. Our initial height, we'll call it d sine theta. Do you see that triangle there? I'm just doing this, 1.0 meters, theta. So this height, y, is equal to d sine theta. So our final height is 0. Rotational inertia of a disk, we have to look that up. If my memory is correct, it should be 1/2 mass of the disk radius squared, but let's look it up. Solid cylinder about a central axis. So notice it's telling you the axis it's rotating about because it matters. I equals 1/2 mr squared. Okay, so my memory was good on that one. So I equals 1/2 mr squared. And then one other thing, I have omega and I have v. For objects that are rolling smoothly, what is the connection between v and omega? Alyssa. Good. V equals r omega for smoothly rolling objects. So with that said, I hate to see malfunction go. So with that said, let's write down 1/2 mv squared plus 1/2 rotational inertia of the disk times omega. So omega is equal to v over r. So this is v over r squared minus mgd sine theta is equal to 0. So notice we have a mass in every term, so they cancel. Notice we have an r squared and an r squared. I'll multiply everything by 4 to get rid of the denominator. So when I do that, this is 2v squared plus v squared minus 4 gd sine theta equals 0. All I did was multiply everything by 4 to get rid of this denominator here. So that is 3v squared is equal to 4gd sine theta. V is equal to the square root of 4/3 gd sine theta. Oh, by the way, square root of g times a height. Does that look familiar?
Very familiar.
Okay. So again, a reality check for us that we're probably pretty close, if not right on the money. So, and in this situation, unless I made a silly algebra mistake, we should be right on the money. Now notice if it were slipping down the plane. So let's just do this really quick conceptually if it were slipping. So I'm not going to really write everything down. So if it were slipping down the plane, like if the plane were ice or frictionless, this term would be 0. So let's eliminate this term. That term is 0. That term is 0. We don't have this contribution. When we solve that, that would end up being the square root of 2g d sine theta. Or in other words, square root of 2gh, which we know that already, because if there's no other forces, it's going to be the square root of 2gh. So look at this. What this is telling us is the object that rolls down the plane is going to be moving slower at the bottom than the object if it were to just slip down the plane. And the reason why is some of the energy has to go into just getting it to rotate. So this value is smaller than this value. This value is 1 1/3 gt sine theta, while this is 2 gd sine theta. Any questions on this one? Yes, sir?
So you use the friction as the rotation. Because you said it's equal to 0, but friction is 1.
No, I didn't say friction is equal to 0. I said the normal force is equal to 0.
Yeah, I mean there. Because we usually do friction as work.
But remember I said, so see this line?
Yes.
I said friction, we're going to say it contributes to kinetic rotational kinetic energy. So this is the contribution to friction.
But if it's sliding, then the friction should be there.
You're talking about what I said verbally? If it's sliding, then we're saying there's no friction, as if it were ice or a frictionless surface. So sliding meaning, so let's consider it a frictionless surface where there's no other forces. If there's no forces to get it to rotate, then it's just going to slide down without rotating. And so in that situation, friction would be 0. And if friction is 0, then this becomes way simpler and we end up with this. And you've done problems like that. I mean, you've done blocks sliding down a plane, blocks weren't rotating, and if the plane were frictionless, you ended up with square root of 2gh.
If you had a rolling friction, it would be right?
Yes, it would.
Yeah.
Yes. And then, and the thing with rolling friction, yeah, and then the distance in which rolling friction is acting. It would be on the right-hand side. And there's a reason why I'm kind of hand-waving here. I'm getting you to trust me on this because we haven't gotten to the point where I can show you how static friction is tied into that. So I'm acknowledging that I'm asking you to trust me, that if we use conservation of energy with things that are rolling smoothly, instead of the work done by static friction, put it into change of rotational kinetic energy. Later, you'll see why that is. I just can't talk about it quite yet. Any other questions?